Hey guys, this is a new series separate from the Leak Code series, which I know is pretty boring, but this is gonna have a lot more structure. Um, this series is gonna be about pretty much just learning Rust, uh, and the way we're gonna break this down is this is gonna be, I'm gonna start off with a month-long Rust journey. The first week is going to be about basic foundations as well as the mental model. The second week is going to be uh, the WASM and edge computing landscape. And the third week is going to be systems design as well as streaming. And then the last week, the fourth week, is just going to be actually building with projects. And that's going to be it for the Rust series. Um, You might see on my page or be familiar with the Leak Code series, which really doesn't have too much structure. I'm just following the Leak Code 150 roadmap. But this one I'm going to try to have a little more structure. And I'm also thinking about adding one more series to this channel. So I'll be streaming a couple of times a day. And that would probably be a purely system design series. So my total day of streaming could look like at around 5 to 6 hours of Leak Code, around 2 hours of system design, and probably another 2 hours of Rust learning. Um, it sounds like a lot, but definitely could make it work. It's only about 9 hours in total, which honestly isn't too bad. Factor in, about 8 hours for sleep, 17. That gives me about, 7 hours to kill if you don't factor in anything else. But yeah, I am a student and I am working two part-time jobs, so there could be some days where I have less time than others. But yeah, so without too much being said, let's get started. I built this schedule. Oh, 1 second. Let me open up chat. Where is it? Tools? Nope. Docs. There we go. Chat. Hi, chat. Oh, what's up? What's up, G6R? Uyung G6R. Welcome in. All right. With that being said, let's go through this. On the left side, on a different monitor, I'm gonna be. Actually, I'll just do it on this page. I can write notes on this page. Let me see. All right. Google Notes. Do you have that? Nope. All right. Let's just use OneNotes. Actually, yes. I don't understand why Google does not have a OneNote feature. That is that's just so surprising to me. I feel like they could definitely get a large share of the student market if they had a good notebook feature like Microsoft has with OneNote. Hi, I'm your biggest fan. Why, thank you, thank you. I appreciate it. All right, so we're gonna call this section Rust. I like the emoji. Um, oh, how do we do this? This is actually a really cool feature that I found out recently. Oh. Okay, so this first Catalog is going to be about REST foundations and the mental model. Yeah, and this is going to be the start of this week. Okay, sounds good. We're going to go over this article that we see on the left. And did you just dab on me? Nice. Okay. We're going to go over this article on the left, spend about a little bit, maybe 1 hour reading various introductions for as to what REST is, as well as look at a cool, helpful introduction YouTube videos. So let's start our first hour. Let me pull up the link. Okay. Okay, so let's go over this introduction. There are many guides and introductions to REST. This one is something different. It is intended for the experienced programmer who already knows many other programming languages. Well, I mean, I guess that's me, experienced programmer. But yeah, I try to be comprehensive enough to be a starting point for any area of Rust, but to avoid going into too much detail except where things are not as you might expect. Also, this guide is not entirely free of opinion, including recommendations of libraries and tooling. Okay. Alright, let's start off with our first section. Rust is a compiled language. Rust's execution model is imperative, with strict evaluation, except there are types that embody a lazy evaluation. Rust is statically typed with an algebraic type system. It supports generic types and generic functions. Monomorphization and dynamic dispatch are both supported, chosen at the point where a generic type is referred to. Type inference is supported in some contexts, especially local variables. Rust is memory safe and thread safe, but with a clearly defined and well-used unsafe escape hatch. Concurrency is supported by multi-threading, and alternately via a green threads-based async system. Concurrent Rust programs are still memory safe. There is no garbage collector. Stack objects are explicitly defined and automatically deallocated. Heap objects are explicitly allocated and automatically deallocated when the references go to scope. Rust has a novel memory and object lifetime management approach with lifetime-based aliasing and mutability rules. There are two macro systems for metaprogramming: a pattern matcher, macro rules, and a very powerful system of arbitrary code transformation. There are fully supported stripped-down profiles of the Rust standard library without OS functions, such as alloc, and without even a memory allocator, such as core, for use in embedded situations. The concrete syntax has many influences. The basic function and expression syntax resembles Bracy languages, but with some wrinkles. Notably, parentheses are not required around the control expression if, etc., but the brackets are required around the controlled statement block, and presence versus absence of a semicolon at the end of a block is highly significant. There is little meaningful separate compilation. The usual aggregation of the Rust libraries making up a single Rust program involves obtaining all of the source code to all of the libraries and building them into a single executable with static linking. There is a good FFI system to talk to C and libraries for convenient interfacing to C++, WASM, Python. Hold on, let me search up how to say. How do you say WAS? Oh, awesome. WASM. Okay, WASM. WebAssembly. So instead of WebAssembly, I'm gonna say WASM. 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 Okay, cool. Generally, dynamic linking is still used for FFI libraries. The unit of compilation is large, the crate, not file or module. There is one principal implementation, Rust C, which is maintained by the Rust project itself, alongside the specifications and documentation. Compilation is slow by comparison with many other modern languages, but the runtime speed of idiomatic Rust code is extremely good. Code generation to native code or WebAssembly or WASM is currently done via LLVM. How do you say LLVM? How do you say LLVM? Okay, well, it's just low-level virtual machine. Okay. But projects to allow use of GCC and Crane Lift are both at an advanced stage. There is also an IR interpreter used mostly for validation. There is no formal language specification. The Rust reference has most of the syntax, but usually lacks important information about semantics and details. The standard library documentation is excellent and comprehensive. For unsafe code, which plays with raw pointers, etc., the semantics are formally but unofficially described in stacked borrows, and programs can be checked by MIRI, the interpreter for the Rust mid-intermediate representation. Rust is available in stable, beta, and nightly flavors, and tends to avoid, and in practice generally does avoid, breaking existing code which was using stable interfaces. There is excellent support for cross-compilation. The project provides an online playground for playing with and sharing small experiments. This is heavily used as a stable way to share snippets, repros, etc., including in bug reports. Obtaining Rust is canonically done with RustUp, a pre-packaged installer/updater tool. RustUp's rather alarming curl bash install rune is mitigated by the care taken by the RustUp maintainers. However, you will also end up using cargo, which is more of a problem. Library ecosystem. Rust relies heavily on its ecosystem of libraries, aka crates, and its convenient but security-wise troubling language-specific package manager, Cargo. It is not practical to write any but the smallest programs without using external libraries. Conversely, the library ecosystem is rich and generally of high quality, although slightly lacking in certain areas, especially webby areas when compared with more webby languages. I'm going to make the assumption that they're talking about JavaScript over here. But the Rust ecosystem contains some exceptional and unique libraries, which can conveniently provide advanced capabilities found elsewhere only in special purpose or research languages, if at all. The combination of static linking of Rust libraries with heavy use of monomorphist generic code can lead to very large binaries. The Rust project has robust and mature governance and review processes. The compiler implementation quality is high, and the project is exceptionally welcoming. Notable ideological features of the Rust community are a strong desire to help the programmer write correct code, including a desire for the compiler to take responsibility for preventing programmer error, pride in helping users write performant code, effective collaboration between practicing developers and academic programming language and formal methods expert. There is also a strong desire to help the programmer with accessible documentation and useful error messages, but generally ease of programming is traded off in favor of correctness and sometimes performance. That is the introduction of Rust. And wow, that was pretty heavy. Let's open a new tab and watch this next video rest in 100 seconds. That's another one I want to watch by Fireship. And then after this, we're gonna watch Rust for JavaScript developers. So let's open that up just now. Okay, so this is a
This is this video is
this is really loud. To understanding Rust types.
this is a video about Rust, and
Okay, so let's watch this video. Let's watch this video and then we can check out the rest of this playlist. But let's see. Today we also have a environment setup planned, as well as a first Rust program being run a little bit later. So we'll probably finish at around 1:30. So we might not, we'll probably watch these Rust videos later, because shortly after this Fireship video and this Let's Get Rusty video, we are going to write our first program and set up our Rust environment. So yeah, that'll be fun. Okay, cool. Let's watch this video.
Rust, a memory-safe compiled programming language that delivers high-level simplicity with low-level performance. It's a popular choice for building systems where performance is absolutely critical, like game engines, databases, or operating systems, and is an
Wait, I want to check real quick. How old is Rust? Rust, created in stable systems. Oh, okay, 2006 is Rust, and I know Python's one of the oldest programming languages. So cool, yeah. Oh shoot, Python. Wow. Okay, yeah. So why do people want to use Rust? I guess it'll be answered in the question, but I just want to know real quick, just for just to know real right now. For its unique combination of high performance and strong memory safety. So what? Oh yeah. What's a garbage collector? This probably is a dumb question, but oh my God, no. In programming languages, yes. Garbage collection is a term used in computer programming to describe the process of finding and deleting objects which are no longer yeah, so anything that's not used, it's deleted. Okay, but Rust doesn't use that. Okay, cool. How does Rust work without a garbage collector? Rust manages memory without a garbage collector. There's ownership system which uses strict rules enforced at compile time. Okay, so at compile time, the memory is free deterministically when it's no longer needed. So at compile, Memory is free deterministically when it's no longer needed, typically when a variable goes out of scope, preventing leaks and dangling pointers. Alright.
Excellent choice when targeting WebAssembly. It started as a side project of Graydon Hoare in 2007, who named it after the Rust fungus. It was sponsored by Mozilla in 2009 and has been ranked the most loved programming language every year since 2016. Mozilla in 2009-2007, who named it after the Rust fungus. It was sponsored by Mozilla in 2009 and has been ranked the most loved programming language every year since 2016, with its fans being known as Rustaceans.
Dang, it's been ranked the #1 most programming languages since when?
In WebAssembly.
Sorry,
It started as a side project of Graydon Hoare in 2007, who named it after the Rust fungus. It was sponsored by Mozilla in 2009 and has been ranked the most loved programming language every year since 2016.
Dang, so since 2016. But this video was made in 2022, so most loved programming language. Let's see. So Python's the most desired language to work with, but Rust is the most loved. I guess that's because the developers that are coding in Rust are really hardcore, and they probably vote the most. That's probably a small bias, a population bias, I guess. And a lot of the Python devs probably don't care too much about ranking their language that they're coding in. They probably just want to go home.
With its fans being known as Rustaceans. Traditionally, high-level languages provide a garbage collector to nerf your control over memory management, while lower-level languages provide functions like free and allocate to shoot yourself in the foot. Rust takes a different approach. It has no garbage collector, but achieves memory safety with a concept known as ownership and borrowing. By default, every variable in Rust is immutable. This allows values to be used in the stack memory, which has minimal performance overhead. However, mutable values or objects with an unknown size at compile time are stored in the heap memory. Every value in a Rust program is assigned to a single variable known as its owner. When that variable goes out of scope, the memory allocated to it is dropped automatically. In some cases though, you may want to pass a reference to a different part of the program. Borrowing allows you to access a reference in memory without taking ownership of it. There are a ton of rules to go along with this system that the Rust borrow checker will validate at compile time. These rules keep your code safe while providing absolute control over performance. Rust also has a package manager called Cargo, where each individual package is a crate. To get started, install Rust, then run cargo new from the command line. In the main.rs file, you'll find a main function, which is where the program will start executing. Declare a variable with let, followed by its name and type. The value can't be changed or reassigned by default, so add mut to make it mutable. The name of the variable is the owner. A reference to its location in memory can be borrowed by other parts of the program by prefixing it with an ampersand. Then use a macro like printline to log the value to the standard output. Rust also comes with a standard library that contains modules to handle I/O, the file system, concurrency, among many other things. Now compile your code to an executable with the Rust compiler. You just built a memory-safe executable that can handle the most performance-intensive system requirements. This has been Rust in 100 seconds. Hit the like button and subscribe if you want to see more short videos like this.
That was a good video. I enjoyed that. Yeah, let's watch the next one.
There's one thing.
Are you still there, my biggest fan? That's been dabbing on the heaters. One second. Okay, yeah, let's watch this. Rust for Dummies in 12 minutes. Perfect video.
All these languages have in common. They suck. So you should learn Rust. But learning Rust is like trying to get a PhD in compiler theory while getting kicked in the balls repeatedly. unless you have a clear guide that maps all the features you already know and love from other languages to Rust. Welcome to Rust for Dummies, where I'll explain all the confusing Rust concepts you need to know to be an effective Rust developer in terms that even a JavaScript developer will understand. By the end, you'll not only get Rust, you'll start preaching Rust to all your coworkers unsolicited like a true Rustation. This video is part of a series for the upcoming official launch of my Rust Live Accelerator, the all-in-one Rust Live training program designed to help you land your first Rust job and become a high-performing Rust developer. The exact official launch date will be announced very soon. To join the waitlist, pause this video right now and visit letsgetrusty.com/join. Part 1. Why Rust code doesn't break. You know those bugs that only show up in production? Seg faults, data corruption, mysterious system crashes? Rust eliminates those. At compile time, no garbage collector, no performance hit. But how does Rust achieve this? A C or C++ developer's biggest nightmare is double-free or use-after-free errors, which can cause your entire program to crash, or worse, corrupt data silently. A double free occurs when you deallocate the same memory twice, which can corrupt the heap. And a use after free happens when memory is accessed after it's been freed, leading to undefined behavior. The problem is manually freeing memory is extremely error prone. In contrast, higher level languages prevent manual memory management bugs by introducing a garbage collector. This is an added background process that automatically frees memory after it's no longer used. This seems convenient, but garbage collectors are notorious for causing intermittent performance issues at runtime, as a garbage collector may pause one or more threads to reclaim memory. This is the type of unpredictable performance hit a systems programming language simply cannot afford. Luckily, Rust has a compile time solution to deal with memory management without incurring any runtime overhead. A brilliant system called the ownership model. In Rust, each value has a single owner. In this case, the user1 variable owns a user instance and controls the lifecycle of the value. When user1 goes out of scope, the value will be automatically dropped, all predetermined at compile time. But what happens when you reassign the value from user1 to user2, for example, or even pass the value into a function? Who ends up owning the value?
1 second, I need to lower the brightness. It's hurting my eyes. My bad. Oh, I can't adjust it. Great, okay, it's fine.
In this example, the ownership of the underlying value gets transferred first from user1 to user2, and then from user2 to user3. And lastly, the user value gets dropped at the end of the function when user3 goes out of scope. Once ownership moves, the previous variable no longer claims the ownership of the underlying value, and it can no longer access the value either. This transfer of ownership is called move semantics, and it's really important because it eliminates nasty memory bugs like double free and use after free, which we saw in the C and C++ example before. So ownership and move semantics solve the problem of allocating and deallocating memory without manual memory management or a garbage collector. But ownership is only a piece of the puzzle. Sometimes you don't want to move or transfer the ownership of a value. For example, let's say we wanted to call print name twice. In this case, attempting to call print name the second time is not allowed, because the ownership of the underlying user value has already been passed to the user3 argument inside the printName function during the first call to print name. What we really want is to give the printName function temporary access to the user instance, while the user2 variable still maintains the ownership. In most other languages, you can hand out temporary access to a value by passing around references or pointers to the value. But the problem with references and pointers is they allow you to do dangerous, dumb, and terrible things like reading and writing to the same value at the same time, mutating shared state without realizing it, or dereferencing a null pointer. The gist is, these languages allow you to do dangerous things with references and pointers. That's how you get weird side effects, data races, and all types of bugs that only show up in production. The good news is, Rust has a clever solution for this as well, called the borrowing model. Rust allows you to gain temporary access to a value using references with a twist. Unlike other languages, references in Rust have certain rules to make sure you don't shoot yourself in the foot. First of all, Rust distinguishes between immutable references and mutable references. Let's go back to our previous ownership example. If we update the printName function to take an immutable reference to the user instance, our code will compile. We can also add an updateName function and have it take a reference. But this time our code doesn't compile, because we are trying to mutate a value behind an immutable reference. To fix this, we have to explicitly mark the user2 value as mutable and update the reference passed to the updateName function to be a mutable reference. Now our code compiles. This explicit labeling of mutable references is great because it prevents accidental mutation. By the way, in the Rust world, a reference is synonymous with a borrow, and referencing is synonymous with borrowing. You'll hear both used frequently. That's why this is called the borrowing model. In our code example, we can say that printName takes an immutable borrow and updateName takes a mutable borrow. So that's the first rule of the borrowing model. The second rule is that you can either have one mutable reference or any number of immutable references at one time. Rust prevents you from using immutable references while a mutable reference is active. For example, if we create two variables, one holding a mutable reference to the user instance and one holding an immutable reference to the user instance, and then pass those references to printName and updateName, we would get a compile time error. The problem is the mutable and immutable borrows overlap. When we call updateName, an immutable reference to the user instance exists, and is passed to the printName function on the next line. This is problematic because the immutable reference is not expecting the underlying value to change. The Rust compiler wants to ensure that when you get an immutable reference to a value, it's guaranteed the value cannot be changed for as long as you hold that immutable reference. The solution is simple. We can define R2 after the call to updateName, or we can simply inline the references like the original example. The third rule is, references must be pointing to valid memory. The compiler ensures this by checking to see if references are used after the underlying value has been freed. References to the user instance are only valid until user1 is dropped. After the user instance is dropped, references are considered invalid and we would get a compile time error if we tried to use them. This system of borrowing gives us the convenience of temporary access to values without the footguns found in many other languages. Okay, so we talked about how Rust prevents an entire class of memory safety bugs through the ownership and borrowing model. But surely Rust can't prevent logical bugs too, right? You know, those bugs you create when your brain isn't braining. Well, actually, it can, to a large extent. Let's see how. Part 2. The genius of Rust's type system. Imagine you update a dependency, some library you're using. There are no errors, everything compiles, so you ship your code and deploy it to the cloud. But then everything breaks in production. Why? Because the library author updated a function or removed a side effect, and your compiler didn't catch any of it. This happens all the time, not because library authors are careless, but because most languages don't give us the tools to express, and more importantly enforce, constraints through code. Let's say we're the ones working on the library and writing a user class in Java. We want to make sure other developers cannot misuse our data structure, so we need to enforce some constraints. First, every user is required to have a name, so our
Okay, it's getting pretty late, so a lot of this is just kind of going in one ear and out the other. So let's just go ahead and create the program after I check out what that is. 3-hour long full course. Oh, maybe this could be helpful and this could be helpful, but this also looks really interesting. So let's see.
Hello and welcome to Rust Programming Language Full Course for Beginners.
This looks really good. I might do this. Let's say tomorrow. Ownership. Da 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 da. Okay, tomorrow I'm going over ownership, and borrowing. So, let's see. All right. Yeah. Let's just.
Everyone's rewriting
Tag that for later.
everything in Rust these days. Discord rewrote their backend and got 10x performance. Dropbox spent 4 years rewriting their sync engine. Microsoft is putting Rust in Windows itself, but Microsoft's own TypeScript team looked at Rust and said, nah, we'll use Go instead. because it was easier for them to port TypeScript to Go. They answered this, but after seeing Rust being brought up in every discussion that isn't even about Rust, it got me curious. Is Rust really that good, or is it just all hype? So I decided not only to learn a good bit of Rust over the past 6 months or so, but take a look at the entire state of Rust in 2025. What it actually is. No hype, no buzzwords, but performance, memory management, things like that. How it compares to other languages, which I did on a smaller scale, but I want to look on a larger scale. Why people are obsessed with it. It is quite literally the most admired programming language. What the actual experience is writing Rust, and where it falls short. Just a whole look into Rust. That's this video. Let's start with the basics. Rust is a systems programming language that promises something that sounds impossible: memory safety without garbage collection. And why is that a big deal? Well, in C or C++, you can do something like this. Pointer equals malloc, free the pointer, then use it again. This compiles fine, but it's a security vulnerability waiting to happen. 70% of Microsoft's security bugs come from memory safety issues just like this. In languages like Java or Python, you don't have this problem because the garbage collector manages memory for you. But that can come with performance overhead and unpredictable pauses. And Rust solves all of this with this little thing called the borrow checker. Here's the same concept in Rust. Create a box, drop it, try to use it. This doesn't compile. The compiler catches the bug before your code ever runs. No runtime overhead, no garbage collector, but also no memory safety bugs. The result is a language that is just as fast as C, as safe as Java, and as expressive as Python. At least that's the promise. Which begs the question, how does Rust actually stack up against these other systems programming languages? I did a quick comparison building a little CLI application in C, C++, Rust, Go, and Zig, and the differences are telling. C gives you raw speed and complete control, but you're managing memory manually with malloc and free. One mistake and you've got a seg fault or a memory leak. C++, on the other hand, adds modern conveniences like vectors and smart pointers. But you're drowning in a bit of complexity. There are like 6 different ways to do basically everything. Go, on the other hand, strips away all of that complexity for simplicity and fast compilation. However, you lose quite a bit of that low-level control and some of the performance. Although people have been arguing with me about this, you tell me in the comments. And then Zig. Zig has so much potential. It's like C, but with better tooling, compile time safety, but the ecosystem is just tiny, and they've been in beta or whatever you want to call it for, I think, 8 or 9 years. And Zig is very low level. Basically, you're shaking hands with the CPU, which you can buy at Micro Center, the sponsor of today's video, which, as you may know, is the best place to buy PC components.
Okay, my power on my screen is gonna cut in about 10 minutes. So I think that's enough, right, for this YouTube
This is
video.
memory safety at compile time. The
So
trade-off
after this
is
YouTube
you're
video,
fighting the
I'm
compiler
probably gonna
up
end
front
stream,
in
but
what seems like never-ending bugs.
so we'll hold off until
that
writing
may
the
just
first
be
program
me.
to tomorrow.
But the alternative is
And remember, tomorrow morning, we're gonna look at some leak code, and then we're gonna look at some system design in the middle of the day, and then we're gonna hop back to leak code, and then end the day off with some of this Rust. But yeah, let's finish this video.
is debugging crashes later, and I would take the borrow checker. All isn't really in your favor. C++ because new projects were not being CLI tools. That's where Rust really shines. Tools like rip, grep, fd, bat, and x 30 years old this year, as did I. Anyway, back to Cargo. So Cargo, the error messages actually really help you. They're really good. They help you fix the problems instead of just telling you something is wrong. But compilation times can be rough. Even small projects take 15 to 20 seconds to compile. Times and traits and generics and macros and async await. Each one makes sense. It's reasonable time someone.
Okay, let's read the comments. interesting. So we could probably.
Here are 3 things I would do completely differently if I was learning Rust from scratch today. Starting with learning Rust by domain instead of by features. When I first started learning Rust, I wanted to go through every single resource, documentation, and book under the sun. But I ended up drowning in concepts I didn't have a need for. Macros, advanced tray bounds, unsafe code, you name it. I eventually realized that instead of trying to learn all of Rust, I should have picked a single domain and learned only the parts of Rust needed to be productive in that context. Rust, CORM or Diesel, etc. So instead, so on. And the best resource.
Okay, so
Rust
learn Rust, but specifically just the parts of Rust related to the reason why you want to get into Rust. So for me, that would be web infrastructure. But yeah, that's probably gonna be the end of today's stream. It's a super short Rust stream. I'm really tired. But yeah, in the morning, I'm gonna be up doing some leak code, and then probably some system design in the middle of the day. I'll try to stream that unless I'm at school, and then afterwards, some more leak code. Then I'll end with some Rust. Yeah, it's been fun.